right, so that's all I really have to say about power at the moment. I think you guys pretty much should remember that from last year, but we could definitely talk about it more in depth in class on Monday if we need to. So now let's talk about our potential energy. And last year we talked about potential energy as being an energy of position. So I know last year we talked about PE equaling mgh, but on the AP test and in subsequent physics classes when you get to college, we use the letter U to denote potential energy, and we use the letter K to talk about kinetic. So last year we learned that the potential energy is equal to the mass times the gravity times the height. So another way to think of this is a way for us to talk about the potential that gravity has to do work on us. This is what we call gravitational potential energy. There was another kind of potential energy we talked about last year called elastic potential energy. And that's the potential energy that is stored in springs and things that bounce. So with elastic potential energy, which is oftentimes denoted as, I think it's like UK or UX sometimes, but that is 1/2 kx squared. All right, so like I said before, we just learned that work can change the kinetic energy of an object. But we also have to keep in mind this idea of conservation of energy. So if something is changing its kinetic energy, it's also going to be changing its potential, because a loss in kinetic energy is going to be a gain in potential and vice versa. So we sometimes will talk about the work done on an object not as being equal to the change in the kinetic energy, but more as being equal to, if I can get my pen back, the loss in potential, or the negative of its potential energy. So conservative versus non-conservative forces. I think your book kind of goes about this explanation in a little bit of a crazy way, but I think it might be better if I just explain it to you, just give you an example. So with a conservative force is any force that when it brings an object back to its original position, the work done on it is 0. So let's take an example of maybe like riding to the top of a mountain in a ski lift. So as you go up to the top of the mountain, this is you, by the way. As you go up the mountain on the ski lift is doing work on you, and it's the work done by the lift would equal to mgh. Now, I'm losing my ink. The work done by the lift would be equal to mgh, and the work done by gravity would be equal to the negative of that value. Now, when you ski back down the same mountain, you're essentially returning to the exact same point that you were at when you got on the ski lift. So in that case, as you go down the side of the mountain, gravity's going to do work on you again. That's going to be equal to positive mgh. So the fact that the work done by gravity when you return to your initial starting position is actually 0, that means that gravity can be considered a conservative force. It's also important to note that if you have two people and they're going to hike to the top of a mountain, let's say this guy takes the direct path, but this guy takes a more winding path, as long as they end up in the same position, the work done is going to be the same, right? Because potential energy is a factor of your position or your height. So as long as they've gone to the same location, their potential energies are going to be equal. This is the opposite of a non-conservative force, which really the only non-conservative force that we have to really talk about would be like friction. The friction is always acting in the opposite direction of motion. So the work it always does will be negative, so it will never have a positive or a zero work because its work is always a negative number. Okay, so let's talk a little bit more about this idea that work is equal to change in U. So remember from before that we said work is the integral of the dot product here, or the force function with respect to the displacement. So we can consequently say this expression as well, that the change in potential is going to be equal to the negative integral of this function here. Again, we're going to go back to our idea of gravitational potential energy and say that whenever we're talking about objects near the Earth's surface, their potential energy is determined by this expression, which you guys already know. Now, the only important thing to remember about this is that this is depending on the reference point that you choose. So let's have an example of what that means. So let's say you're on a diving board 8 meters above the ground. Your mass is 75 kilograms. So what is the potential energy of the student, if this is the student? They've got a big head, apparently. And this is 8 meters high. So if we choose the potential energy to be 0 here at the ground, what is the student's potential energy on top of the diving board? So this is just 75, 10 times 8 for that first one. And then whenever we do the subsequent ones, we're going to have to take into account, this is 6,000 joules. So on the next one, U is chosen to be 0, 4 meters above the ground. So instead, our 0 point is right here, which means that instead of actually being 8 meters above the ground, she's only 4 meters above our reference point. So that would be 75, 10, and 4, which would be 3,000. And then what if the potential is chosen to be 0, 10 meters above the ground? So now she's actually below the 0 point by 2 meters. So it would be 75 times 10, negative 2, which would be negative 1,500 joules. So always keep that in mind whenever you're dealing with some problems. You have to be very mindful of the reference point. Alright, so spring force is another example of a conservative force because it will do work on a block or an object, but when the object returns to equilibrium, it's returning to the same spot that it started from, so the work done on it will be 0. So, I guess it's probably a little bit easier. This is going to be your expression for the potential energy of a spring, which 1/2 kx squared. And this is equal to the integral of your spring force. So remember that we had that your force is equal to negative kx. This is your Hooke's law expression. And remember that we said that the integral of f ds will give us our work, and that the negative, don't mind that, the negative integral of that will give us our potential. So if this is our function for our force, we can plop that guy in there, and we get negative kx with respect to dx. Now we can, let me get an eraser here. Now when we integrate that value, we get 1/2 kx squared. Which is where this expression comes from. Okay, there's some stuff on the next slide, but we're going to kind of go through it pretty fast because I essentially just did the stuff that's on the next slide. Now, all right, potential and kinetic energy graphs. I just want to point this out to you guys because I have seen on the AP tests sometimes where they make you sketch these pictures just so that you understand what's happening to the potential energy of a system or the kinetic energy of a system. So potential energy, if we take this point here to be a point of equilibrium, whatever point that may be. And we can think of this graph kind of as being for a spring and a block attached to it. So as it oscillates back and forth, what's going on with the object's potential energy? So potential energy is 1/2 kx squared. And I'm sure that you guys can tell either from putting this in the calculator or just from experience, this is going to give you a parabola, an upward facing parabola. When the displacement is 0, you have no potential energy. So if this is like your displacement and the y is your potential energy. And you're going to get a parabola happening on either side. So you're going to have the maximum potential energy when you have maximum displacement on either side of your graph. Now, a kinetic energy graph, which we'll get into a little bit more in the next chapter when we talk about conservation of energy and such. But kinetic energy graphs are drawn the opposite, right? Because kinetic energy, you have maximum kinetic energy whenever you are at a situation when you are furthest away. You have maximum kinetic energy when you are at equilibrium. When I stretch this block out here and let it go, when it comes back through the center, that's when it has lost all of its potential energy and has gained all of its kinetic. So this graph here would be the graph for a potential energy, and this graph here would be the graph for kinetic. And that's all I have for you guys this weekend, and I will talk to y'all on Monday.